What if I told you that faster-than-light travel isn't just difficult, not just technologically out of reach, but fundamentally impossible? Not now, not in 1,000 years, not ever. For decades, we've been promised warp drives, hyperspace jumps, and instant travel across the stars. Science fiction tells us it's only a matter of time before humanity breaks the light speed barrier and spreads across the galaxy. But what if that belief is a fantasy? What if the universe itself has built-in rules that no civilization, human or alien, can cheat? Tonight, we're going to examine why traveling faster than light may not just be unlikely, but why attempting it might actually break reality itself. And if that's true, what does it say about our future in space? Before we go any further, it's important to be clear about what this video is, and what it is not. This is not a NASA said so, therefore it must be true argument. It's not blind trust in institutions, space agencies, or popular science personalities. In fact, skepticism is the entire point. The idea that faster-than-light travel is impossible doesn't come from press releases or government talking points. It comes from something far more uncomfortable, the internal logic of physics itself. For over a century, physicists, many of whom strongly disagreed with one another, have independently arrived at the same conclusion. From Einstein's theory of special relativity, to modern quantum field theory, to experimental particle physics, every successful model of reality contains the same hard limit. Not because engineers haven't tried hard enough. Not because we lack imagination. But because the equations describing space, time, energy, and causality stop working the moment faster-than-light motion is allowed. And this is where healthy skepticism matters. Real science isn't about believing comforting stories of future empires among the stars. It's about asking whether an idea survives ruthless testing. Faster-than-light travel has been tested, mathematically, experimentally, and philosophically, and every time, it fails in the same way. Not gently. Catastrophically. Independent researchers, not tied to space agencies or sci-fi dreams, have shown that even hypothetical faster-than-light particles create contradictions that physics cannot tolerate. Cause comes after effect. Information arrives before it's sent. Reality begins to fold in on itself. So when you hear phrases like, future technology will solve it, or, we just don't understand it yet, that isn't scientific humility, it's often wishful thinking. Skepticism doesn't mean rejecting science. It means following it even when the answer is disappointing. And if the speed of light truly is a fundamental limit, built into the structure of the universe, then no amount of funding, innovation, or belief will ever change that. When most people hear the phrase, speed of light, they imagine a very fast number. Roughly 300,000 kilometers per second. A technical challenge. A record waiting to be broken. But this misunderstanding is where nearly every faster-than-light fantasy begins. The speed of light is not the maximum speed of photons. It's the maximum speed at which reality itself allows information, cause, and effect to propagate. In other words, light doesn't move fast because it's special. Light moves fast because space-time is built that way. To understand this, we have to stop thinking like engineers and start thinking like physicists. The speed of light, often written simply as c, isn't about propulsion, fuel, or engines. It's a structural feature of the universe, woven into the geometry of space and time. No matter where you are, no matter how fast you're already moving, no matter how advanced your technology becomes, this number stays the same. That alone should raise suspicion. In everyday life, speeds add together. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing still sees the ball moving at 150. But light doesn't behave that way. If you chase a beam of light at 99.9% the speed of light and turn on a flashlight, the beam still pulls away from you at exactly the same speed. Not faster. Not slower. The universe refuses to let that number change. This isn't a technological limitation. It's a rule. Einstein realized that in order for the speed of light to remain constant for all observers, space and time themselves must become flexible. Length contracts. Time slows. Simultaneity breaks down. And these effects aren't theoretical. They've been measured repeatedly with atomic clocks, satellites, and particle accelerators. As objects with mass accelerate, they don't just move faster through space. They are forced to move differently through time. This is the part science fiction usually skips. Every object is always moving through spacetime at the same total speed. When you're sitting still, you're moving almost entirely through time. As you speed up through space, your motion through time slows down. Clocks tick more slowly. Processes drag. Aging itself decelerates. As you approach the speed of light, something extreme happens. Time dilation increases without limit. To outside observers, your clock slows more and more. From their perspective, you never quite reach the speed of light. You just get closer, forever. This is why everything with mass is trapped below the light speed barrier. Not because engines aren't powerful enough, but because there is no spacetime state in which a massive object can exist at light speed. At that point, time for that object would completely stop. And objects with mass cannot exist in a timeless state. Light can do it because light has no mass. Photons don't experience time. From their own perspective, if such a perspective can even be said to exist, the moment they're emitted and the moment they're absorbed are the same event. Zero time passes. That's not a trick we can replicate with technology. This brings us to the most common misconception of all: just add more power. In normal life, more power means more speed. Push harder, go faster. But relativity breaks that intuition completely. As you approach light speed, additional energy doesn't significantly increase your velocity. Instead, it goes into resisting further acceleration. Spacetime itself pushes back. You can pour in energy endlessly and still never cross the threshold. The universe isn't saying, "Not yet." It's saying, "Not allowed." And once you understand that the speed of light isn't a speed limit imposed by technology, but a boundary defined by the structure of reality itself, the idea of casually surpassing it starts to look less like future engineering, and more like wishful thinking. Once we understand that the speed of light is not just a fast number, but a structural limit built into spacetime, the next question becomes unavoidable. What actually stops us from reaching it? The answer isn't heat. It isn't fuel efficiency. It isn't material strength. It's energy, specifically, how much energy reality demands as you approach light speed. In classical physics, acceleration is simple. Apply a force, gain speed. Double the force, double the acceleration. There's no upper boundary, at least not in theory. Relativity destroys that simplicity. As an object with mass accelerates, something strange happens. Its resistance to acceleration increases. Not because the object is getting heavier, in a mechanical sense, but because spacetime itself is changing how that object responds to force. The closer you get to the speed of light, the more energy is required to squeeze out even the tiniest increase in velocity. At first, the effect is subtle. At 10% the speed of light, you barely notice it. At 50%, it becomes measurable. At 90%, it becomes severe. At 99.9%, it becomes absurd. Each additional decimal place costs exponentially more energy than the last. This is the infinite energy wall. Mathematically, the energy required to accelerate a massive object to the speed of light approaches infinity. Not very large. Not astronomical. Infinite. And infinity is not a number engineers can work around. No future fuel source changes this. Matter, antimatter annihilation doesn't fix it. Zero-point energy fantasies don't fix it. Perfect efficiency doesn't fix it. Even converting an entire planet into pure energy wouldn't be enough, because the requirement doesn't scale linearly. It diverges. This is why phrases like advanced propulsion are misleading. Propulsion systems don't fail because they're inefficient. They fail because the destination itself is unreachable for anything with mass. A useful analogy is trying to climb a hill that gets steeper the higher you go. At first, progress is easy. Then it becomes exhausting. Eventually, every step forward requires more energy than the last. But this hill doesn't just get steeper, it becomes vertical, then overhangs, then stretches upward forever. No matter how strong you are, you never reach the top. And here's the key point skeptics often miss. This wall appears before light speed is reached. Long before. Practical limitations emerge well below C. Radiation losses increase. Structural stresses rise. Time dilation grows extreme. Engineering challenges pile up on top of a barrier that was already impossible in principle. This also explains why particle accelerators, our most powerful machines, never push particles to light speed, even though they dump enormous energy into them. Instead, particles asymptotically approach the limit. More energy just makes them harder to accelerate, not meaningfully faster. Nature demonstrates this every day. And this is where the idea of just going faster than light collapses under its own logic. To cross the light speed barrier, you would have to already be traveling at light speed in order to surpass it. But there is no physical process that allows a massive object to reach that state in the first place. It's not a locked door. It's a wall with no surface to stand on. Which leads to an even deeper problem, because even if you could somehow bypass the energy barrier, the consequences wouldn't stop there. In fact, breaking the light speed limit doesn't just challenge engineering. It challenges cause and effect itself. And that's where the universe becomes truly hostile to faster-than-light travel. Up to this point, faster-than-light travel might sound merely impractical, outrageously expensive in energy, brutally unforgiving to engineering, but still a technical challenge in principle. This is where that illusion ends. Because once you allow anything to move faster than light, you don't just get a faster spaceship. You get a universe where cause and effect no longer behave consistently. And physics cannot tolerate that. To understand why, we need to talk about time, not as a ticking clock on a wall, but as a dimension intertwined with space itself. In Einstein's universe, space and time form a single structure called spacetime. Events are not just somewhere, they are somewhere and somewhen. And the speed of light defines how these events can influence one another. Light speed isn't just about motion. It's about which events are allowed to be connected by cause and effect. If event A can influence event B, there is a limit to how fast that influence can travel. That limit preserves the order of events for all observers, no matter how they're moving. Break that limit, and the order collapses. Here's the unsettling part. In relativity, two observers moving relative to each other can disagree about whether two distant events happened at the same time. That's already strange, but it's harmless as long as no signal travels faster than light. Once faster-than-light motion is allowed, that disagreement turns deadly. A signal sent faster than light in one frame of reference can arrive before it was sent in another. Not metaphorically. Literally. Cause comes after effect. This isn't a philosophical problem. It's a mathematical one. The equations demand it. With faster-than-light signals, it becomes possible, at least in principle, to send information into the past. And once information can travel backward in time, paradoxes aren't optional. They are guaranteed. You could receive a message telling you not to send the message you're about to send. You could observe an effect with no identifiable cause. You could prevent the conditions that allowed the signal to exist in the first place. Physics doesn't get confused by this. It simply stops working. Every predictive model we rely on, from particle interactions to thermodynamics, assumes causality. Effects follow causes. Information doesn't arrive before it's created. Break that assumption, and the entire logical framework collapses. This is why physicists say that faster-than-light travel doesn't just violate relativity, it violates reality's self-consistency. Time dilation already hints at this instability. As an object approaches light speed, time slows relative to outside observers. At light speed, time effectively stops. Beyond light speed, the math doesn't describe slower time, it describes reverse time. That's not science fiction interpretation. That's what the equations imply. And this is why hypothetical faster-than-light particles, called tachyons, were largely abandoned. Not because they were experimentally inconvenient, but because their existence destabilized the entire causal structure of spacetime. If tachyons existed, there would be no universal now. No reliable sequence of events. No guarantee that the past stays past. Some people argue that the universe might protect causality in ways we don't yet understand. And in a sense, it already does. The speed of light appears to be that protection mechanism. It's the universe's way of saying, you can move, but you cannot outrun cause and effect. This also reframes faster-than-light travel as something more than ambitious engineering. It becomes an existential threat to coherent reality. A universe that allows faster-than-light signals is a universe where prediction, memory, and even identity become unstable. Science itself becomes impossible, because experiments could influence their own outcomes retroactively. And that leads to an uncomfortable conclusion. The reason faster-than-light travel seems impossible isn't because we're too primitive. It's because a universe that allowed it wouldn't be stable enough to exist in the first place. And yet, despite this, you'll often hear that loopholes remain. That clever geometry, exotic matter, or space-time manipulation might let us cheat the rules. So next, we need to confront those supposed loopholes head-on. Because if faster-than-light travel is ever claimed to be possible, this is where the argument usually hides. At this point in the discussion, faster-than-light travel often retreats into a familiar hiding place. If we can't outrun light, if we can't power through the barrier, if causality collapses the moment we try, then the argument shifts. We won't move faster than light, we're told. We'll move space itself. Warp drives, wormholes, space-time shortcuts. On paper, these ideas sound like elegant loopholes. In reality, they are where speculation begins to drift away from physics and into mathematical fantasy. Let's start with warp drives, specifically the Alcubierre drive. This concept doesn't propel a ship through space. Instead, it compresses spacetime in front of the ship and expands it behind, carrying the vessel along inside a bubble of distorted geometry. Inside the bubble, the ship never locally exceeds the speed of light. Technically clever, physically disastrous. The first problem is energy, not just how much, but what kind. To create a warp bubble, the equations require something called negative energy density, often referred to as exotic matter. This isn't just energy we haven't learned how to produce yet. It's energy with properties that violate known energy conditions, the rules that prevent spacetime from behaving wildly. Small amounts of negative energy do appear in quantum effects like the Casimir effect, but these are fleeting, microscopic, and tightly constrained. They cannot be scaled up, stabilized, or shaped into engineering tools. A warp drive doesn't require grams of exotic matter. Early estimates demanded more negative energy than exists in the observable universe. Later revisions reduced the amount, but only by assuming idealized conditions and ignoring destabilizing effects. Even optimistic models still require unphysical matter that may not exist at all. Then there's stability. Warp bubbles aren't gentle distortions. They produce extreme tidal forces at their boundaries. Any particle crossing the edge would be violently accelerated, potentially releasing catastrophic radiation. The bubble itself would be vulnerable to quantum instabilities that could cause it to collapse unpredictably. And collapse isn't benign. Depending on the model, a collapsing warp bubble could release energy comparable to high-energy astrophysical events, not exactly something you want happening near your destination. Now let's talk about wormholes. Wormholes are hypothetical tunnels connecting distant regions of spacetime. They appear as solutions to Einstein's equations, but so do many things that nature seems to forbid. Most wormhole solutions are either unstable or collapse instantly unless held open by, once again, exotic matter with negative energy. Even if such matter existed, traversable wormholes create the same causality problems as faster-than-light travel. Move one mouth relative to the other, and congratulations, you've built a time machine. This isn't speculation. It's a direct consequence of relativity. And time machines aren't just inconvenient, they're radioactive to physics. They introduce paradoxes so severe that many physicists believe the universe actively prevents their formation. This idea is sometimes called the chronology protection conjecture. In simpler terms, reality appears to censor its own loopholes. There's another uncomfortable detail rarely mentioned in popular explanations. These concepts exist because mathematics allows them, not because nature endorses them. Einstein's equations are permissive. They describe what could exist under certain conditions, not what does exist. Without physical evidence that exotic matter can be created, controlled, and stabilized, warp drives and wormholes remain mathematical curiosities, not engineering blueprints. And there's a deeper pattern here. Every proposed workaround to faster-than-light travel requires piling impossibility on top of impossibility. Infinite energy. Negative energy. Perfect control of quantum gravity, a theory we don't even have yet. At some point, Skepticism demands we ask a hard question. Are these real solutions, or are they elaborate ways of avoiding an uncomfortable conclusion? That the universe doesn't just make faster-than-light travel difficult. It makes it self-destructive. And just when some people think quantum mechanics might rescue the dream, that maybe information already moves faster than light in subtle ways, another misconception enters the conversation. So next, we need to dismantle one of the most persistent myths of all. At this stage, when relativity seems to slam the door shut, many people turn to quantum mechanics, hoping it quietly unlocked a back entrance. You've probably heard the phrase, quantum entanglement allows instant communication. Particles affect each other faster than light. Spooky action at a distance. If any part of modern physics sounds like it might rescue faster-than-light travel, this is it. But here's the uncomfortable truth. Quantum mechanics doesn't break the light speed limit. It reinforces it. Quantum entanglement is real. It's been experimentally verified countless times. Two particles can be prepared in a shared quantum state such that measuring one instantly determines the outcome of the other, even if they're separated by vast distances. That sounds like faster-than-light influence. But influence is not communication. And this distinction is where almost every popular explanation goes wrong. When you measure one entangled particle, you don't choose the outcome. You can't encode a message into it. The result is fundamentally random. The other particle's state becomes correlated, but no usable information has traveled between them. To confirm that entanglement exists, the results from both sides must later be compared using ordinary, slower-than-light communication. No comparison, no message. This isn't a loophole, it's a built-in safeguard. Physicists call this the no-communication theorem. It proves that quantum entanglement cannot be used to send signals, commands, or data faster than light. No matter how clever the setup, no matter how advanced the technology, the math blocks it completely. Spooky.
Yes.
Useful for FTL travel?
No.
Some argue that future discoveries might change this, that deeper layers of quantum reality could allow controllable non-local effects. But here's the problem. Every experimentally verified version of quantum mechanics, including quantum field theory, the most successful theory in science, is constructed to respect relativistic causality. Break that, and the theory becomes internally inconsistent. In fact, quantum mechanics and relativity already coexist in a fragile balance. Allowing faster-than-light information transfer would shatter that balance instantly. And once again, we see a pattern. The universe seems perfectly happy to allow strange, counterintuitive phenomena, as long as they don't let information outrun cause and effect. Even hypothetical quantum teleportation doesn't help. Despite the name, nothing actually teleports faster than light. Quantum teleportation still requires a classical signal to complete the process. Without it, nothing meaningful happens. No shortcut. No hidden channel. No cosmic cheat code. This is why claims about quantum consciousness, quantum signaling, or quantum propulsion almost always collapse under scrutiny. They rely on vague language, misunderstood experiments, or outright exaggeration. Quantum mechanics doesn't weaken the light speed limit. It enforces it with surgical precision. And when you step back and look at the full picture, relativity, energy constraints, causality, space-time geometry, quantum mechanics, something becomes clear. The universe isn't accidentally hostile to faster-than-light travel. It's systematically hostile. Every foundational theory we trust agrees on this one point. Not because physicists conspired. Not because imagination failed. But because allowing faster-than-light motion would unravel the very structure that makes a coherent universe possible. Which brings us to the most uncomfortable part of all. If faster-than-light travel is impossible, not just for us, but for anyone, then what does that say about our place in the cosmos? About alien civilizations? About interstellar exploration? And about the stories we've been told for decades? If everything we've covered so far is true, if faster-than-light travel is not just impractical, but fundamentally forbidden, then a series of deeply uncomfortable questions immediately follow. Because the implications don't stop at engineering. They reach into astronomy, astrobiology, and even the stories we tell ourselves about humanity's future. Let's start with the obvious one. If nothing can travel faster than light, then interstellar travel becomes brutally slow. Even reaching the nearest star system takes years, decades, or centuries. Entire human lifetimes pass between destinations. Supply lines become impossible. Communication becomes delayed beyond usefulness. The dream of a sprawling interstellar civilization begins to collapse. No galactic empires. No interstellar trade routes. No rapid rescue missions between stars. Just enormous, isolating distances. This forces a hard re-evaluation of something many people take for granted, that advanced civilizations naturally spread across the galaxy. What if they don't? What if the universe isn't empty because no one else exists, but because no one can go anywhere fast enough to matter? This reframes the famous Fermi paradox. Instead of asking, "Where is everybody?" we're forced to ask something more unsettling. What if everyone is stuck? Stuck in their home systems. Stuck behind relativistic barriers. Stuck watching the universe from afar, just like we are. Suddenly, the lack of alien visitors doesn't require elaborate explanations. No hidden conspiracies. No cosmic catastrophes wiping everyone out. Just physics. And this is where space skepticism enters dangerous territory, because it challenges narratives many people find comforting. If faster-than-light travel is impossible, then the idea of routine interstellar missions becomes questionable. Grand claims about humanity spreading through the stars start to sound more like speculative mythology than realistic planning. It also raises awkward questions about how space exploration is framed to the public. Why are we so often promised futures that quietly ignore relativistic limits? Why does science fiction bleed into science communication? And why are inconvenient constraints so rarely emphasized? Skepticism isn't cynicism, it's consistency. If the laws of physics forbid fast interstellar movement, then any claim implying otherwise deserves scrutiny. Not dismissal, scrutiny. And this extends beyond aliens. It forces us to confront a psychological question. Why are we so attached to the idea that distance doesn't matter? Perhaps because accepting limits is uncomfortable. Because a universe with hard boundaries feels smaller. Because the idea that we might never escape our cosmic neighborhood feels claustrophobic. But discomfort isn't evidence. The universe doesn't owe us adventure. It doesn't care about narrative arcs or destiny. It operates on rules, and those rules don't bend to optimism. And here's the most unsettling thought of all. If faster-than-light travel is impossible, then the future of civilization may not lie among the stars, but inward, toward sustainability, longevity, and survival within tight constraints. That's not a failure. But it is a radically different future than the one we've been sold. So the question becomes, are we prepared to confront a universe where limits are real? Where expansion is slow? Where imagination must submit to evidence? Or will we continue clinging to fantasies simply because the alternative feels too small to accept? There's one final step left in this discussion. Not to offer comfort. Not to offer solutions. But to ask whether our beliefs about the future of space say more about us than about the universe itself. So, where does this leave us? After examining relativity, energy requirements, causality, theoretical warp drives, wormholes, and even quantum mechanics, the picture is surprisingly consistent. The universe doesn't just make faster-than-light travel hard. It makes it impossible. Not because we're unimaginative. Not because we lack technology. Not because someone decided to keep the stars out of reach. Because the rules of reality themselves prevent it. And that realization can be unsettling. For decades, humanity has imagined itself hopping from star system to star system, exploring distant worlds, and meeting other civilizations. Sci-fi and popular culture have embedded these ideas deeply in our collective imagination. But understanding these limits forces a different perspective, one rooted in evidence, critical thinking, and humility. It doesn't mean the universe is small. It doesn't mean exploration or discovery is meaningless. It means our scope is defined by the true nature of reality. It means we have to grapple with what is physically possible, rather than what feels exciting in a story. This is also a call to skepticism. Every claim about cheating physics, new propulsion miracles, or hidden shortcuts to the stars deserves scrutiny. Popularity or hype doesn't override the fundamental constraints we've seen. And perhaps most importantly, This is a call to reflection. What does it mean to live in a universe with real limits? How does it change how we approach space, technology, and our own ambitions? How much of what we've dreamed of the future comes from reality, and how much comes from comforting wishful thinking? Physics doesn't dictate how we feel, but it does demand honesty about what is possible. The stars are still out there. Our curiosity, ambition, and ingenuity are still out there. But they operate within a cosmos that has boundaries, and learning those boundaries is itself a profound kind of exploration. So next time you hear someone promise faster-than-light travel, or interstellar empires, or instant cosmic shortcuts, remember, the universe has already answered. The question isn't whether humanity can reach the stars instantly. The question is whether we can accept the universe as it truly is, and find meaning, purpose, and discovery within the limits reality sets for us. Because accepting limits isn't defeat. It's clarity. It's wisdom. And in the end, it's the only way to navigate the cosmos responsibly.